So the first problem of this tutorial concerns itself with a very nice property of the wave functions for one-dimensional problems, bound state wave functions. So consider any wave function which is a solution of the Schrodinger equation for some potential v of x, which is a bound state wave function which has the property that psi of x goes to 0 as x goes to plus minus infinity. Okay, and for this kind of solution, you're asked to show that the solution is necessarily non-degenerate, which means that there cannot be two wave functions with the same energy eigenvalue E. Okay. If you do have such a situation, then it is necessarily true that the two wave functions are not linearly independent of each other. Okay, so our goal is to try and show that if there is degeneracy and if there is two wave functions psi1 and psi2 that correspond to the exact same energy E, then psi1 and psi2 should be linearly dependent on each other. Okay, so knowing psi2, I should figure out psi1. So it's not necessarily two distinct wave functions. So the way you go about this is to simply set up the Schrodinger equation. So the time independent Schrodinger equation. Let me assume that there is two wave functions, psi1 and psi2, both corresponding to the same energy eigenvalue E. Psi1 double prime, which means d squared psi1 over dx squared. Okay, E psi1, and minus h bar square over 2m psi2 double prime plus v of x psi2 equals E psi2. Let me call this equation 1, and let me call this equation 1 and equation 2. Okay. So I'll do a small trick. I will multiply the first equation by psi2, and I'll multiply the second equation by psi1. E psi2 psi1. And multiply this equation, equation number 2 by psi1. So this gives me this is equation 4. So if you look at equation 3 and equation 4, and if I take the difference of these two equations, notice that the potential term and the energy term both drop out. Okay, if I take the difference, so 3 minus 4 would imply that psi2 psi1 double prime minus psi1 psi2 double prime equals 0. I can throw away the overall constant because the whole thing is equal to 0 anyway, which I can write as ddx of psi2 psi1 prime minus psi1 psi2 prime equals 0. Okay. So the second equality follows from, because the cross term, which is psi2 prime psi1 prime, will cancel between the two terms. So the first equation and the equation below it are identical. Okay. So which means that this combination of wave functions is equal to a constant. So this, if I integrate this, I mean, I get that this is equal to a constant value. Okay. So I integrate and I show that psi2 psi1 prime minus psi1 psi2 prime equals some constant C. Okay. But I can actually go further and determine what this constant is. Since the right hand side is a constant, it has to, the left hand side should be equal to C no matter where I evaluate this quantity. So I'll evaluate it at x is equal to infinity. Evaluate at x is equal to plus minus infinity. If I evaluate at plus minus infinity, obviously the left hand side is 0 because I'm dealing with bound state wave functions that vanish at x equals plus minus infinity. This tells me that the constant C is actually equal to 0. Which means psi2 psi1 prime is actually equal to psi1 psi2 prime, which I can rearrange as psi1 prime over psi1 equals psi2 prime over psi2. Okay. And I can trivially integrate this first order differential equation to show that psi1 of x is equal to some constant times psi2 of x. So in other words, if I start with the assumption that psi1 and psi2 are two wave functions that each correspond to the same energy eigenvalue E, then I finally land up with the assertion that these two are actually equal to each other up to a constant. So they are not really linearly independent, which means psi1 and psi2 are linearly dependent and hence are not two unique solutions. Okay, this tells us that in one-dimensional problems in quantum mechanics, there cannot be any degeneracy. The solution is straightforward, but it's actually a very important theorem that helps you solve certain other problems with ease. Are there any questions about this? If there is any questions, please unmute and ask. Otherwise, I'll move on. Questions? Okay. So the second question is on the simple harmonic oscillator. And you are asked to calculate the product of the uncertainties, calculate delta x, delta p in some state n. Okay. So remember that delta x equals the expectation value of the square of the operator minus square of the expectation value of the operator square. Okay. Similarly for delta p. So to calculate the product of the uncertainties, we need to figure out the average values in some state, okay, of x square and x. So I showed yesterday in the class quickly that the average value of x is equal to 0, but I will repeat that very quickly. Remember that x can be written as an addition of the A and A dagger operators, and P can be written as the difference between the A and A dagger operators, okay, excuse me, where the quantity beta, which has the units of inverse length, is given by square root of m omega 0 over h bar. So the average value of x, in expectation value of x in any state, is simply n x n, which goes like n a plus a dagger n. Okay, so a acting on the state n gives you the state n minus 1. A dagger acting on the state n gives you n plus 1. So this has two terms, n minus 1 plus n plus 1 with some constants, but both are equal to 0 because the states are orthogonal to each other. So this is equal to 0. For the exact same reason, the expectation value of p is also equal to 0. Okay. So our only task is to calculate the expectation value of x square and p square. So let's do that. The expectation value of x square is the square of x is 1 over 2 beta square n a plus a dagger square n. Okay. Now we should be careful in evaluating terms of this kind. So you should do the squaring properly. So this is equal to n. Remember that in haste, you should not write this as 2 times a dagger. You should write this as two different terms because a and a dagger do not commute. So this is equal to a square plus a dagger square plus a dagger plus a dagger a acting on n. Okay. For the same reason as outlined before, a dagger square acting on n would give you n plus 2, and the overlap of n and n plus 2 would be equal to 0. And a square acting on n would give you n minus 2, and the overlap of n and n minus 2 would be equal to 0. So these two terms won't contribute. Okay? So we are left with evaluating a dagger and a dagger a. But I can use the commutation relation a dagger equals 1 to write a dagger as 1 plus a dagger. Again, if I'm doing this too fast, please stop me. So the expectation value of the x square operator can be written as 2 beta square n 1. So instead of a dagger, I will write 1 plus a dagger a, and there is another a dagger a times n. Okay, a dagger a is nothing but the number operator. So the number operator acting on n simply counts the number of particles in that state. So my x square is 1 over 2 beta square n 1 plus 2n n, which is nothing but 1 plus 2n number divided by 2 beta square. Okay, are there any questions about this average value or the expectation value of x square operator? The p square expectation value can be done similarly. P square would be minus m omega 0 square over 2 beta square times expectation value of m. Remember, this is a minus a dagger. Again, the a square and a dagger square will not contribute. So you will have minus a dagger minus a dagger a acting on n. And I can take the minus outside, which cancels with the minus here. So this is again equal to m omega 0 square over 2 beta square times 1 plus 2. So delta x, which is square root of the x square expectation value minus expectation value of x square, is simply the square root of this guy. So this is equal to 1 over beta times square root of 1 plus 2n over 2. And delta p is equal to 1 over beta times, I can also pull out m over 2, 1 plus 2n. Okay. And if I take the product of these two uncertainties in any general state n, delta x, delta p is given by 1 over beta square times 1 plus 2n divided by 2 times, what do I get? Omega 0 times square root of n. Is that right? Yeah. But notice that my beta is square root of m omega 0 over h bar. So beta square is m omega 0 over h bar. Sorry, p square should be m square omega square. That's where I made a mistake. So this is 1, and I can pull out the factor of m omega also. So if I plug in beta square as m omega 0 with h bar, the m omega 0 cancels, and I get delta x times delta p is 1 plus 2n divided by 2 times h bar, which I can write as h bar. If I pull out the factor of 2, which cancels, n plus 1 half. Okay. Is this clear? If it is not clear, please unmute and ask, or just write in the chat. But clearly, the state for which this is the least is the state for which n equal to 0, which is the ground state. So the product of this uncertainty is least. Oops. Delta P is minimal for the state n equal to 0. And for this state, delta x times delta P is equal to h bar over 2. But notice that this is the absolute minimal value this uncertainty product can take, which corresponds to a Gaussian. But as we saw in the lectures, the ground state of the simple harmonic oscillator is indeed a Gaussian, so everything is consistent. Ground state of the SHO is a Gaussian. Okay, and this product can be the least only for the Gaussian. Okay, so this is the general statement of this problem. And notice that in the language of A and A dagger, computing expectation values is actually much simpler than if you use the position representation and evaluated the integrals. So that is another advantage of using the Dirac notation in this particular problem. Any questions? Oh, not a very active session is this, huh? Okay.
It's clear, sir.
Okay. How many of you attempted the next problem? How many? Anybody? Can somebody tell me what it is that is being asked? Lokesh? Mahesh?
Sir, values of mu and lambda for which it will be Hermitian.
So can you tell me what the values should be?
Sir, we can take either of this given Hamiltonian and we can restrict the values of mu and lambda.
Excellent.
So lambda will be 1 and mu will be something 1 minus.
It doesn't have to be 1. It just tells you, it is just asking you what are the constraints of mu on mu and lambda. Remember, your first step is correct. So take this h, which is mu a dagger a plus lambda a plus a dagger. So the dagger of this would be, remember that mu and lambda in general can be complex. So this should be mu star, and the dagger of a dagger a is a dagger a because this is automatically Hermitian, plus lambda star times a dagger plus a, which is the same as a plus a dagger. So if I want the Hamiltonian to be a Hermitian quantity, I want the first line and the second line to be the same. H equals h dagger implies mu equals mu star and lambda equals lambda star. That's what it says, right? Otherwise, the two equations will not be identical. That tells you that mu and lambda should be real quantities. Because if something is equal to the complex conjugate of itself, then obviously the quantity is completely real. Okay? So that is the constraint on mu and lambda the problem places. The second part of the problem says, for a suitably chosen operator B, can you redefine the operator such that the Hamiltonian can be recast as some simple harmonic oscillator plus a constant? This is looks a little tricky, but it's fairly straightforward. All I'm trying to ask is, can there be another linear operator related to A, such that when written in terms of this new linear operator, the Hamiltonian takes a much simpler form? So let me try. Let me say that A, or yeah, let me say that I can define a new linear operator B, which is A plus some constant. Okay, when I say A plus some constant, this should be interpreted as A plus C times the unit operator. Okay. Now it can be some other complicated operator also, but this is the simplest choice that I can guess. So let me first look at the simplest choice that I can guess. And the goal is that if I sort of suitably adjust C, then I might be able to rewrite this Hamiltonian in the much simpler form that is given there. If this choice does not work, then we have to go for a more complicated operator C. Okay. So for now, I'm simply using a simple shift A plus something times the unit operator. Let's see if this works. So this tells me that A is B minus C. Okay. So let me simply substitute this in the Hamiltonian. H equals mu times A dagger would be B dagger minus C star. A would be B minus C plus lambda times B plus B dagger, minus C star. That is what it is. Okay, is this clear? Interestingly, I lost one student once I started asking questions to you guys. Huh. Now,
Yes, sir.
It is clear? Okay.
Yes, sir.
So I can write this as mu times B dagger B. Now I'll collect the terms linear in B. B times, there is one factor here of lambda, and there is another factor from the first term, which is, what is it? Minus mu C star. Plus, I'll collect the terms linear in B dagger. There is one term from the second guy and another term from the first guy, which is mu times C. Minus lambda C plus C star. Okay, it's exact same equation. I've collected terms which are linear in B and B dagger also. Now I want this to be a very simple Hamiltonian that looks like a simple harmonic oscillator Hamiltonian. So I don't want terms linear in B and B dagger. To get rid of these terms, I need to impose some conditions on C, but C is a constant. I can always choose the constant to be whatever I want. So I will simply choose C to be lambda over mu, which is a completely real quantity. If I choose C to be lambda over mu, remember that the second term and the third term both drop out, right? So I can rewrite my Hamiltonian as mu times B dagger B minus lambda C plus C dagger, C plus C star would be 2 lambda over mu. So this is equal to mu B dagger B minus 2 lambda square over mu. That is all. Okay. So what are the eigenvalues of this operator? Can somebody tell me? What is the spectrum? Anybody?
म्यू एन
Mu n?
हाँ बस
नहीं, second term भी है ना? So this is basically mu n minus this constant. This constant will just come along, that is all. Okay, mu n is correct, minus 2 lambda square over. This will be sort of shifted, that is all. Okay, because the energy eigenvalues of B dagger B is just n, mu times n, and this shift will automatically appear because it is a constant piece in the Hamiltonian. So you can always add or subtract this constant piece. So En would be mu n minus 2 lambda square over. That will be the spectrum of this Hamiltonian. Good. Any questions?
Sir, can we have another form of B cap?
Can you have another form of
Operator B.
operator B? I'm sure you can, but it is unnecessary. This is the simplest choice and it works. The problem is if you have a more complicated choice, so look at the second term and the third term, this term and this term. It turns out that one condition on C can make both these terms equal to 0. Okay, if you have a more complicated operator, that might not work. You understand? So
Yes,
instead, you can simply start by saying A is some B minus some other operator, C operator, and then figure out the constraints on the C operator. And if you can work it out, then that is well and good. It will be some other constant that is shifted, that is all. But in this case, we got lucky because the same choice of C lambda over mu gets rid of both the linear terms in B and B. Okay.
okay.
Sir,
Yes.
can you please explain again why we want the second and third term to be 0?
Oh, so that is the question, right? Show that for a suitably chosen operator B, the Hamiltonian can be written as mu times B dagger B plus a constant. So I want to write the Hamiltonian in the form B dagger B plus a constant. So I don't want terms in linear in B and B dagger. So I want to get rid of these terms because that's what the question is asking me.
Yeah, okay, sir.
How many of you attempted the last problem? So in the last problem, I actually made a typo. The U should actually be time evolution in quantum mechanics is exponential minus IHT over H bar, not plus. So there was a typo there. Hopefully you caught it. If not, I'm telling you now. So I will make a small change in the solution of this question. The last line I say, using the above and taking H to be that of the 1D simple harmonic oscillator, calculate the commutator of X at unequal times. Instead of 1D simple harmonic oscillator, let us take the free particle Hamiltonian. I'll tell you what the difference is as we go along. Okay. So let us look at the first half of this problem. The first half of this problem is define the Heisenberg equation, Heisenberg operator using U dagger, Schrodinger operator, where U is given by exponential minus IHT over H bar. So now, since AH is explicitly time dependent, you want to figure out the equation of motion. How does A change, evolve with respect to time? So let us differentiate this guy. This is equal to, remember that the Schrodinger operators are time independent, only the Schrodinger kits are time dependent. So this is equal to du dagger dt ASU plus U dagger AS du dt. Okay. So what is du dagger dt? ddt of e to the minus IHT over H bar is simply equal to minus IT over H bar e to the minus IHT over H bar. Okay. And similarly for ddt of e to the plus IHT over H bar. So pay attention to the steps. This is important. This will be equal to, sorry, not IT. I made a mistake. Somebody should have pointed it out. This is minus IH because I'm differentiating with respect to time, right? So what's the first term? The first term would be minus IH over H bar e to the minus IHT over H bar AS e to the IHT. So, okay, let me simplify my calculations and simply use U and U dagger. So this is equal to minus IH over H bar times U. Okay. So this will be equal to, or U dagger. U dagger ASU. And the second term would be, yes.
U dagger change हो जाएगा ना plus iota.
Plus कैसे हो जाएगा? हाँ, U dagger change हो जाएगा. Sorry. This is very good. Thank you. Okay, makes sense. Thank you. The second term would be plus u dagger as, and ddt of this guy would be minus IH over H bar. So remember that U times IH over H bar is the same as IH over H bar times U, because U is also a function of the Hamiltonian. The Hamiltonian commutes with itself. Okay. So the last term, I can write this IH over H bar either to the left of U or right of U. They are both the same. So I'll take advantage of this fact and I will write this whole thing. And this, whatever is remaining, this U dagger ASU is simply the definition of the Heisenberg operator. So this is equal to IH over H bar AH minus I over H bar AHH, which I can write as if I pull out the minus I over H bar, this should be the commutator of AH and H. And this is the same as, okay, so these are the Heisenberg equations of motion for the corresponding operator. Any questions about this? Yes or no? Is this clear?
Clear, sir.
So the second part, so I'll take my Hamiltonian, instead of simple harmonic oscillator, I'll take my Hamiltonian to be the free particle, E square over 2. Oops. Free particle Hamiltonian. Okay. Now you're asked to calculate a very interesting commutator x at T1, x at T2. Obviously, in the Schrodinger picture, the commutator of x with itself is equal to 0. But in the Heisenberg picture, it turns out that the commutator of x with itself at unequal times is not equal to 0. Okay, so we will work this out and then talk a little bit about what it implies. So first, how do I calculate how to calculate xh at some time t1? So let me look at the equation of motion. So instead of ah, plug in, instead of a, look at x. So this will be dxh dt equals 1 over IH bar xh h. Okay. So let's write this out. This is equal to 1 over IH bar. What is this? This is e to the IHT over H bar XS e to the minus IHT over H bar H. Okay. Notice that the Hamiltonian parts commute with the Hamiltonian. It is only the XS that doesn't commute with the Hamiltonian, because XS, the Schrodinger operator X, does not commute with the Schrodinger operator P. X comma P is IH bar. So I can write this commutator as 1 over IH bar. I can pull out the e to the IHT, e to the plus IHT over H bar to the left hand side, and e to the minus IHT over H bar on the right hand side using the trick that I taught you before. And I write this Hamiltonian, and I write this commutator as okay, like that. Is this clear? Any questions about this? If you don't trust me on this, just expand the entire thing out and you'll find the exact same thing. So write this as e to the IHT xs e to the minus IHT times h minus h times the entire thing, and you'll find that this is the same as this, because h commutes with e to the IHT. So what is this? Xs times h, which is p square over 2m, is nothing but 1 over 2m. So remember that this is also Hamiltonian is also written as p square. So I'll suppress the S here. And I'll write this as P x comma P plus x comma P P. This is something I've already done, so I will not do it in detail. I'm sure you understand. So this is IH bar. So this is 2IH bar P over 2M or equal to IH bar P Schrodinger over M. So the time evolution of the X operator in the Heisenberg picture is given by 1 over IH bar e to the IHT over H bar, this term, times the commutator, which is IH bar P Schrodinger over M, and this term e to the minus IHT. The IH bar cancels, and the 1 over M can be pulled outside. And whatever remains is basically the definition of the Heisenberg operator P. Okay. So if you look at it closely, you would see that this is starting to resemble more and more the classical equation of motion. The dx dt is P over M. It is just in the Hamiltonian dynamics, this is the time evolution of X, for example. Is this clear? So notice that even if I did not take the free particle Hamiltonian, up till now I'll get the exact same result. Why? Because even if I add a potential V of X here, the V of X will commute with X anyway. So my commutator will not change and this result will not change. So this is regardless of whether I'm talking about a free particle or a particle that is moving under some potential V of X. This part does not change. The reason I'm taking the free particle is because the integration becomes now non-trivial. So what do I mean by that? See, if I formally have to integrate this, XH at some time t1, assuming that I start with time t equal to 0, would be given by 0 to t1, 1 over m ph dt. Okay. What is this? This is equal to 1 over m integral 0 to t1 e to the IHT over h bar P Schrodinger e to the minus IHT over h bar dt. Make sense? Yes or no?
Yes, sir.
Okay. See, up till now, things have been very general, regardless of which potential I'm talking about. But here is where the free particle thing helps me out because I have to integrate this guy. And this is in general a little tricky because there is no reason P has to commute with the Hamiltonian. Because if I take the Hamiltonian as P square over 2m plus V of X, then I have to be very careful with this integration. I have to work it out completely and then integrate whatever comes out. But if it is a free particle Hamiltonian, then I can be a little cavalier because free particle Hamiltonian does not have the V of X. And P commutes with P, so I can simply pull the P to the left-hand side. Does this make sense? So this is why free particle is the easiest case to evaluate in this case. Even though I'm sure you can also do it for the simple harmonic oscillator, but you have to work a little bit. So since H is P square over 2m and PS commutes with PS anyway, I can write down XH of T1 as 1 over m. If I pull out the P Schrodinger, because it's also time independent, so I can put it on the left because it commutes with the Hamiltonian. And if I pull it, and I can also pull it outside the integral because it is time independent, I get 0 to T1. This is simply U dagger U dt, and U dagger U is just 1. So XH T1 is simply given by 1 over m ps times the time t1 plus a constant. How do I evaluate the constant? I evaluate the constant by looking at time t equal to 0. At time t1 equal to 0, Of course, the first term is equal to 0, and the Heisenberg operator time t equal to 0 is exactly the Schrodinger operator. So this constant has to be x0, which is the Schrodinger operator x. So I can write down the solution of xh formally as 1 over m p Schrodinger times t1 plus x0. Are there any questions about this? So doing this integration out would be a little tricky if I took some other Hamiltonian. Even though every step up till here would be identical, even if I take some other Hamiltonian. Here, free particles sort of helps me a little. So if I have the same guy evaluated at some other time t2, obviously the first term will change to t2 plus x0. So notice that the first and the second operators do not commute because they are functions of both p and x. And since p and x in the Schrodinger picture do not commute, xh at time t1 and xh at time t2 do not commute. Let's evaluate this commutator. xh at t1, xh at t2 is equal to 1 over m plus x0, comma 1 over m plus x0. And what are the two terms that are non-zero? Well, p commuting with x0 is non-zero, x0 commuting with p is non-zero. So I get two terms, t1 ps x0 plus 1 over m t2 x0 ps. Remember that x0 is just xs, the Schrodinger operator x, and this is just ih bar. So this whole thing is equal to ih bar over m times t2 minus t1. Okay. Which means the commutator of x in the Heisenberg picture at two different times do not commute. They are not compatible observables. Okay. So if you actually calculate what delta x is in this picture, delta xh for the operator in this picture, you would actually find that this is proportional to the time difference. So what does this mean? This means that even if you can make delta x very, very small at one time, as time keeps growing, as the time difference keeps changing, the wave packet keeps spreading out, which is something that you know already. So the position, even if you constrain the particle at one particular time, as time evolves, the packet will keep spreading and you will lose knowledge of the position. That is what this means in the Heisenberg picture. So you have to be a little careful, and if you have not seen this before, it would be wise to work it out yourself completely and satisfy yourselves that this is indeed right. Okay. And if you want a challenge, try to work it out for the case of h equal to p square over 2m plus 1/2 m omega square x square. The simple harmonic oscillator. See if you're able to do it. That'll be an interesting exercise. Okay. So formally, that is the end of tutorial number 7, and I hope you guys had a chance to look at it and are now well versed in these one-dimensional problems. Are there any questions about any of this? Any questions? Okay, so if there is no questions, I will stop at this point and we will meet in class tomorrow. Okay.